Let's reset the lens distortion value. We simply select a different method and load a reference frame with the captured distortion grid. Right-click and create a new reference camera. Go into the camera and load the still with the distortion grid. This is what a properly shot distortion grid looks like. Take a good look and make sure to teach others. The culture of capturing distortion grids is still weak, even though it's one of the most important tasks in on-set supervision. To put it simply, a distortion grid is a perfectly flat surface with a checkerboard pattern. The software knows this checkerboard is meant to be straight, with all squares having equal sides. Based on that, it can calculate the lens distortion. How should a grid be captured? The camera must be perpendicular to the surface of the grid. All four corners must be clearly visible in the frame. Let me say it again. This is the ideal example of how a distortion grid should look. A picture has already been shared in chat showing how not to shoot a grid. Something like that is absolutely unacceptable. It might be funny, but you'd be surprised how often this kind of thing actually happens. On a serious note, why is that incorrect? Because the grid needs to fill the whole screen. If it's just a piece of paper that clearly bends, it's useless. Funny or not, this will not help you calculate distortion, for the exact reasons mentioned. The entire point is that we're filming a flat surface, and by observing how a flat surface gets distorted, we can reverse that distortion and make the image flat again. Let's do it. I'll close the timeline for now. We don't need it at the moment, and I'll switch the viewer to distortion grid controls mode. If we look at the camera settings block related to the distortion grid, what can we see here? We can change the color of the grid that we're about to overlay onto our captured distortion grid. You can enable any color, but this is mostly useful in cases where the grid blends into the image and gets lost against the captured distortion grid. In our case, red works just fine. Matrix snapping mode is the mode that determines the type of distortion grid we're working with. More precisely, it's the structure the program will recognize when aligning the grid to the distortion reference image. There are two options, checkerboard and lines. Let me show you an example. For example, this is what a distortion grid with lines might look like. Why do we need to specify the type of distortion grid? Because we're about to align this grid overlay onto our distortion reference. And now we align, roughly match the captured distortion grid with the overlay grid provided by 3DEqualizer. When lines is selected, the program looks for line intersections. If you select checkerboard, it will look for intersections between black and white squares. Snapping noise limit determines how aggressively the program will try to snap the grid points. The higher the value, the more forcefully the software will try to grab onto something, but it might snap to the wrong point if the image is unclear. The lower the value, the more conservative it becomes. If the match isn't precise enough, the point simply won't snap and will be disabled. It's worth immediately explaining why checkerboard is generally better than lines, even though, at first glance, working with lines might seem easier. At first you might think it's straightforward to snap to line intersections, but that's not quite the case. When you zoom in on a heavily distorted image, it becomes surprisingly difficult to pinpoint the exact center of each line crossing. Right now, it might seem like everything snaps automatically, but when auto-snapping fails and you have to adjust manually, every inaccuracy becomes your problem. And here precision is crucial. That's why it's much harder to confidently identify the exact center at the crossing of two blurred or curved lines. Well, it's much easier to find it exactly at the intersection of the squares. We mark 3 corners. That's enough to define the grid's direction and scale. Of course, you can place all the nodes manually, but it's much easier to use the snap function. Just place one corner of the cell and click the button. The rest of the points will automatically snap to the grid. If needed, you can manually adjust everything afterwards. Let me show you. The same thing works with lines. I'll delete this grid. The rest is pretty straightforward. You just select lines, and the process works the same way. This grid isn't from our shot, so we don't need it here. We switch to a separate camera, switching to the grid. What we do next? We need to expand this grid to cover the entire distortion chart. To do this, go to the menu Edit, Add Points. Also looking ahead, use this button to delete points. Now for the hotkeys, add a row to the right, Ctrl+C, and arrow right. Add a row to the left, Ctrl+C, and arrow left. Up and down, same logic. Ctrl+C, up arrow and down arrow. To extend existing rows, use Ctrl+Shift and the arrow keys in the desired direction. We start adding to the right, and see rows appearing one after another. Our goal is to evenly fill the entire grid, starting from the visible part inside the frame and gradually expanding beyond the edges. Now we add to the left, and right away we see that we've hit an area the program couldn't recognize. That happens. We select that point and simply disable it. And we keep going to the left. Control C and the left arrow. Once again, we start by marking the clearly visible area. No need to go straight to the very edge. Let's gradually move toward the edges. Next, once we've filled in the main part of the grid like this, we can move on to cover the corners. Cells the program can't detect will sometimes be automatically disabled, and that's a good thing. The main concern is to avoid having enabled points that follow the wrong direction. If you see a dashed line, it means that curve is disabled, and in this case, that's exactly what we want. If it were enabled and not aligned with the grid, that would be a problem. Now pay attention. Straight lines should follow the cell edges. Points must sit exactly at the intersections of the cells. Here, for instance, this is a good corner. This is a good corner. This is a good corner too. We can see that this point didn't snap and got disabled. This one isn't quite at the intersection and it's still enabled. Basically, we need to restore this corner because the grid cells here are really small. No matter how carefully you try to shoot a distortion grid perpendicularly with such a wide lens, chances are one of the corners will end up like this. It's just a very wide lens. So in this area, everything falls off into shadow, into vignetting. By the way, we actually have a guide with the team on how to properly shoot distortion grids. First, you can check it out on our YouTube channel. Go to Matchmove Machine channel and then in the videos tab at the bottom, open the video with our guide. Or you can find a guide on our website, matchmovemachine.com, in the tools and knowledge section. First of all, learn to shoot distortion grids yourself. It's genuinely important. If you're a compositor and you're watching this course just to improve your skills, maybe you won't need to shoot grids on set. But if you plan to work on set as a supervisor, knowing how to shoot grids properly is essential. We put effort into this. Let's go to this corner and fix it. First, let's adjust this point. It's snapping completely wrong. If we want to disable automatic snapping, we can do that in the options menu. The item automatically snap on release is responsible for that snapping behavior. Turn it off. Automatic snapping works when adding new points, exactly what we were just doing. Each added row was automatically snapping to the grid template. If this option had been turned off, the points would have just appeared nearby without snapping, and we'd have had to align everything manually. But this really depends on the situation. Right now, we've disabled this option, and as you can see, there's no more snapping. You can place points anywhere, but still, you should try to be as precise as possible. That's the key takeaway here. This point is currently disabled, but we can easily move it to the correct position and enable it again. Here it is, selected. Let's enable it. Basically, what we're doing right now is calculating how much our 2D trackers need to be offset according to this grid. And this also clearly illustrates why it's a bad idea to track this deep into the corners. Sure, we might be able to calculate distortion there approximately, but as you can see yourself, there's definitely room for improvement. Tracking in such corners and then trying to extract distortion from that. So let's say we've done all that. Great, well done. Now we need to calculate the distortion value and transfer it into the lens parameters. Before starting the calculation, make sure the correct lens type is selected. In our case, this option works, but I've already explained them earlier. So in your own projects, go by the type of optics that was actually used on set. One important thing to note, each lens type in the list may have multiple distortion models. For example, an anamorphic lens might have 3 options and a spherical one 2. So what should you do in that case? You can run the distortion solve using different models appropriate for your lens type and choose the one that gives the lowest error, the one where the result works more accurately, and where to look for that error. We'll get to that next. In the Viewer Distortion Grid mode, go to the Calc menu and select Calc Distortion. The corresponding window will appear. On the left, you'll see the distortion parameters, which ones will be calculated and which won't. The ones included in the calculation are highlighted. You can manually add or remove parameters simply by toggling their selection. On the right is the grid itself, which will be used for the calculation. Below is the console window showing the calculation status, along with buttons to start the process. The parameters displayed on the left side of the window depend directly on the selected lens type, so if you choose a different lens model, the set of distortion parameters will change accordingly. That's why by this point you should already know exactly which lens model you're using. If you don't want to dive into the details, you can leave everything as is. By default, the parameters selected are usually sufficient for calculation. In non-standard cases, of course, you can add others, like lens center offset, pixel aspect, cylindrical distortion, or even focal length. But focal length is not calculated from regular grids like the one we're using. For that, a so-called modern grid is required, an additional grid shot at roughly a 45-degree angle to the surface, rather than strictly perpendicular as in our case. Only by analyzing the perspective distortion of the grid cells can the focal length be calculated, but that's a separate topic. In our case, with a regular spherical lens, the current parameters are perfectly sufficient. Click Calc, and the program will calculate the distortion based on how we align the grid. And now we see the calculation status. 6 lens distortion parameters have been optimized for a single frame, meaning one distortion grid. You could have shot several grids for this same lens and selected multiple here. You might have even shot a modern grid, and the final error, around 0.1, is really good. Next, we can either just apply the parameters and close the window, or simply close the window. Let's apply the parameters to the lens and close the window. They've been transferred here. How can we check what we've got? We can click Undistort. Bam. This is what the image looks like after we've undistorted it. So now, in theory, all the cells should be straight. But straight is relative. The grid itself was set up with a slight tilt in this direction. That's why the cells appear larger on one side and smaller on the other. There's some perspective. Still, the shot has now been undistorted, and this is how it looks. Pretty interesting, isn't it? Now let's take a look at our main plate. And to be clear, this isn't the manually eyeballed setup we used earlier. This is the result calculated precisely using the film distortion grid. There's a bit of irregularity here, but that's exactly the point. It's nearly impossible to capture distortion perfectly at the very edges of the frame. Even though in this case the grid was captured quite well, what you can do in such situations is try switching the distortion model and recalculating the grid based on that. We won't be doing that now, but just keep it in mind. Now we can recalculate the camera using the distortion that we captured with the grid. Let's go to the lineup tab and solve the camera again. Well, this looks pretty good.